Roto-Finish Compound is the key to success in several ways. 1. For a distributor, compound is a residual income that pays even when you are home in bed. And 2. Sometimes the right chemistry is the key between success and failure of a process or project. It's a key piece of our business and should be for yours as well. Roto-Finish chemistry sounds pretty simple, perhaps 1 or 2 compounds. Our sales manager talks about 4 different vats of compound: red, blue, green, and yellow. It is much more than that. Roto-Finish chemistry is roughly 3,000 different formulations with approximately 400 active each year. Know your chemicals first and foremost. Safety is critical. Before you start using any chemical, here are some things you should know for your safety, your customer's safety, and your employees' safety. First line of defense is the MSDS or SDS. This is part of the Community Right to Know regulations and tells you how to properly handle the product. Technical data sheets give some generic information about the product, including its pH and any specific hazards. As of 2016, OSHA adopted the Globally Harmonized System of Labeling, GHS. Technical and safety support are available from people who design, blend, recommend, and use Roto-Finish chemistry. Your friendly Roto-Finish chemist. There are few words in the English or work languages that generate as much anxiety as chemistry or chemicals. Many people don't understand and generate a protective wall or mental block whenever they hear the word. Some are paralyzed by panic thinking of their high school chemistry class. Most products are not hazardous. Of the 400 actively sold products, so far this year, less than 10% are considered hazardous. Most of these are in the corrosive category and aren't much more hazardous than some everyday chemicals, but we will get into that later. For many people, chemistry brings to mind the strange alchemist mixing strange concoctions in a medieval laboratory, much like the slide of the Roto-Finish chemist. They picture a witch's cauldron bubbling with black magic, eye of newt, bat wings, and monkey fur. We need to be especially careful with the monkey fur. Personal protective equipment is identified on the SDS and on the product label. For every industrial environment, OSHA requires safety glasses. For some products, corrosive, strong cleaners, and solvents, rubber gloves are required. For extremely corrosive products, a protective coverall or coat may be required. When transferring concentrates or changing our drums, a splash shield may be required. So we've talked a little bit about our product and how to protect yourself from chemical exposure. Now let's talk about why we use chemistry. There are 4 basic elements of mass finishes. Parts, this is the most obvious. This is the reason why we are doing any type of work. Media, in most cases, this is what does the work on the part. Machine, something has to cause the interaction between parts and the media. Compound and water, this is the grease in the gears. This is the material that modifies or smooths out the interaction of the other 3 components. Let's go over the purposes of mass finishing. Deburring, removing sharp edges and small raised edges from cutting, stamping, machining, or shaping parts. Brightening, essentially cleaning and removing surface oxides from the surface of a part, usually associated with burnishing. Cleaning, removing any number of films or soil from the surface of the parts. Descaling, removing heavy-duty oxides from the healing process. The surface film may include carbonaceous residue. Improving or refining, gradually working the surface to a smooth reflection. Inhibiting, leaving a film or residue that protects the part from oxidation. Drying, simply removing all of the liquid residue from the process. Chemistry is involved in every aspect of these purposes of mass finishing. Yes, even drying. Evaporating or absorbing the fluid off the surface is a chemical process. Compound and water's primary job is to keep the media clean. If we are using a ceramic or plastic media, the media does the work of braiding the surface, but if the part is oily and the oil isn't cleaned, the media gets loaded with oil and will not cut. So what does the compound actually do? Wets the surface. In order for any of the chemical process to take place, the surface of the part must be made to be like water so that the waterborne process can work. Cleaning the oil. If there is oil on the part, we have to remove that before we can effectively grind burrs, brighten, or descale. Suspend soils. As we clean the oils and abrade the surface of the part, generating broken down media fines or abraded metal, we don't want this to redeposit on the part and get ground or pinned back into the surface. Generating foam. Foam is important in many processes. It cushions the interaction between the part, media, and machine. It carries the chemistry to recessed areas of the part. Control lubricity. Like any grinding or polishing process, not enough lubricity causes glazing, galling, and rough cutting. Too much lubricity prevents the media from doing any work. Provide cooling. This is more of an issue in high-energy equipment, but excessive heat can result in excessive chemical usage or reduced brightness. Control pH. pH is one of the most important characteristics of a compound. pH is critical in removing scale or oxide, providing a specific shade or color to the metal, and some specific types of cleaning. Controlling water hardness. For many cleaning agents, water hardness interferes with the cleaning agent's working. The cleaning agents clean the water before it cleans the parts and media. Removing corrosion and scale. These are tied to cleaning mechanisms and pH. Controlling the part color. Most metals have a range of colors through a range of pH values. We will discuss this more in depth later. Inhibiting corrosion. Most of the chemistries we design are based on providing some level of corrosive protection. Some are designed specifically to provide long-term protection. In the last two slides, we describe the functions of the compound in the process. 6 of the 13 items are related to cleaning. Cleaning is important and is generally a prerequisite for every other function. You can't brighten an oily part. Let's take some time and talk about how cleaning works. Sequestration and chelation, wetting, emulsification, saponification, solubilization, displacement, dispersion. We will talk a little more in depth about each one in the next few slides. A chelate, or sequestrant, is a chemical that binds primarily with a metal to form a very soluble molecule. Hard water has calcium and magnesium in it in varying amounts. These minerals can react with certain types of soaps to form soap scum. If the soap reacts with the minerals, it can't function as a soap. Chelate and sequestrants react with the minerals to allow the soaps to do what they are supposed to do. Scale and tarnish are oxidized metal. If the chelate is strong enough, it will dissolve the oxide off the surface. If something stronger is used to dissolve the oxide, then a chelate will help hold it in solution so that it won't redeposit and so that it can be flushed out of the process. In some processes, like acid burnishing, tarnishes are dissolved, but parent metal can also be dissolved. For the same reasons stated previously, a chelate reacts with the dissolved metals so that they don't redeposit on the part. The next mechanism, and probably the most important for cleaning, is wetting and emulsification. Let's start with emulsification. What is it? Everyone has heard the phrase, oil and water don't mix. This is accomplished with surfactants and emulsifiers. These are the chemical magic that bridge the gap between water and oil. The reason oil and water don't mix is that one has a chemical structure that is polar, water, and the other is non-polar, oil. Here is a representation of a surfactant, and its unique structure contains both polar and non-polar areas. Picture your part with a drop of oil on it. The oil coats the surface. Now we want to clean the part. If we put the oily part in the water, nothing will happen. In order to clean the part, we add a compound with surfactants. This compound has surfactants in it that disperse in the water. When we submerge the oily part in the compound, the surfactant molecules orient themselves in the oil film. Because the polar outside of the molecule likes the water, it starts to bubble the oil into a droplet form. Eventually the droplets lift off the surface and form a water-soluble droplet oil in the water. These droplets are called micelle, and the end result is emulsification. The characteristic of an emulsion is a generation of a milky solution. The next most significant attribute of the compound is controlling pH. Part color and cleaning effectiveness are tied to pH. pH is a measure of acidity or alkalinity in a system. Steel is moderately affected by pH level of the product being used to finish it. Less than 4 is smutty, between 4 and 9 you get silver and chrome, and above 9 you get gray. To explain a little better. Below a pH of 4, the iron will be dissolved out of the surface, leaving carbon, nickel, and cobalt, and all other components in the surface. At pH values above 9, iron in the surface reacts and forms metal hydroxides. Copper shows the same transition, but much more than steel. Below a pH of 3, there's an etch of the surface that appears frosty pink. Between 3 and 10, there are varying colors of red to reddish orange. Above a pH of 10, the same type of reaction occurs as with the steel, and we form copper hydroxide on the surface. As we talked about, pH is the measure of acidity or alkalinity. In water systems, the pH range is 0 to 14. In oil systems, the range goes much higher, but doesn't have the effect of the higher pH levels in water. pH of oil systems is mostly academic and isn't commercially used. 7 is neutral, below is acid, above is alkaline. pH can be a difficult concept for some people to follow. Firstly, it is a logarithm. This means that if you take a pH of 7 and we change to pH of 6, it is 10 times more acid. For a change from 7 to 5, it is 100 times more acid. I like to put this in perspective with the following list. These are some common things you may recognize. Stomach acid is 0.8. This is somewhere between 1 million and 10 million times more acid than neutral pH of 7. Tabasco sauce is 1.8, or a little over 100,000 times more acid than neutral. Cola at pH of 2.4 would be considered corrosive in industrial applications. Coffee has a pH of approximately 4.8. This makes it a little more than 100 times more acid than neutral. These last two get more reaction than anything else on the list because they are commonplace and surprisingly quite acid. Eye drops at 7.2 are very close to neutral. This is critical because a shift of any more than a few tenths of pH could result in very serious eye pain. So what is neutral? Salt water has a pH of 7.0. Laundry soap, 9.5, represents the basic starting pH of most alkaline cleaners. Ammonia, at 11.9, is almost 100,000 times more alkaline than neutral. Topping off the list at pH 14, Drano. We see the effects of saponification every day, but many people have never heard or seen this word. It simply means soap making. This is the chemical reaction that takes place when animal fats and vegetable-based oils react with alkali and makes the fat or oil soluble in water with surfactant properties. One of the most common is Murphy's oil soap, great-grandma's lye soap. In the past, great-great-grandma or great-great-grandpa used to take the lard drippings from cooking a pig and mix it with ashes from the fire. They found that the fat became thicker and began to congeal. When they tried to wash this congealed residue off, they noticed foam and that things cleaned easier. They later found that vegetable oils did the same thing, and if you heated up beef, bison, or deer fat, you could do the same thing. How does this apply to us today? Saponification is everywhere in our industry. Many aluminum-based machining fluids use vegetable oil-based. Buffing compounds are mostly animal fat-based. When we clean with these alkali cleaners, we saponify them and make soap. Solubilization is another word many people are unfamiliar with, but they understand its effects. Like dissolves like. Petroleum-based oils, greases, waxes, vegetable oils, and animal fats are nonpolar and are soluble in mineral spirits like acetone, lacquer thinner, and other solvents. Salts, surfactants, acid, bases, and inhibitors are polar and are soluble in water and other polar solvents like alcohol and ether. Displacement is physically moving or pushing the residue off the surface of a part. A pressure washer is a good example of this. Other good examples are brushes, rags, or sponges with a bucket cleaner. The following are other common examples in our industry: mass finishing equipment, industrial parts washers, ultrasonic and electrolytic cleaners, polishing, buffing, and brushing. The next attribute of compound is in surface refinement. In this process, a series of steps usually takes a part from a rough surface to a very fine and smooth finish. The chemical requirements are different in each step of this process. Usually we start out with a ceramic media to cut out surface imperfections. A second step is frequently a plastic media or a much finer grade of ceramic. From that surface, we can either paint, plate, or we can continue with more refinement with a burnish polish step. Imagine a part with a rough surface. We scrub the surface with the media and start to grind off the top of the roughness. The roughness is further refined to make the part smoother. In the final step, the part is smooth and is ready for use. Accelerated chemistry is a special type of chemistry and process that greatly reduces the amount of time to accomplish the same amount of improvement. Let's start with the same part. In the accelerated process, the surface of the part is oxidized to a soft film known as black mold. The media easily scrubs off this soft film on the top of the peaks of the surface of the part. The exposed metal is then re-oxidized, but the unscrubbed area stays the same. The oxidation and scrubbing continue. Eventually, the surface imperfections are reduced to the point where the part is smooth, continuing with the oxidation process until all imperfections are gone. Then a burnishing compound is used to clean the oxidation from the surface. The result is a bright, smooth surface. The last attribute of chemistry that we will look at is the inhibition of the part from oxidation. Picture your nice, cleaned, and finished part. You invested time, resources, and energy in finishing the part. Now you want to protect it. So you prepare a solution of inhibitor. Your part gets submerged in the solution with all of these inhibitor molecules in it. When you remove the part from the solution, a film remains on the surface. This film has inhibitor molecules on it. As the water evaporates away from the film, it begins to make a coating. After full evaporation, an inhibitor coating results. You will notice that this is very similar to the cleaning emulsification process in reverse. These two processes are at odds. Cleaners that inhibit or inhibitors that clean are commonplace in the industrial environment. Neither type of product can outperform a product desired to do just one function. A cleaning inhibitor can't clean as well as a cleaner, nor can it inhibit as well as an inhibitor. Hammond Roto-Finish has several resources to help you with the right compound: the selection guide, product descriptions, the price list, and Hammond Roto-Finish experts.